Complete cellular destruction with cryosurgery is dependent upon each component of the freeze-thaw cycle. Extracellular freezing dehydrates a cell, creating a chemical disequilibrium. Further destruction is achieved by freezing the intracellular environment of a cell. The slow warming effects on the cell facilitate the rupture of the membrane, thereby completing the cellular destruction cycle. In order to achieve the highest probability of cell destruction, a cryosurgical device must cause intracellular ice formation at a temperature which is sufficient to induce cell death. Clinical experience and physical constraints suggest that all cells will freeze internally near -50 degrees Celsius. Therefore, the ablative capacity of an ice ball is measured by its zone of maximum destruction, or that area of the ice ball where the temperature is approximately -50 degrees Celsius or colder. The area where the temperature gradient is -50 degrees Celsius or warmer is referred to as the zone of potential viability, or the area where intracellular ice may not form, thus potentially leaving behind viable cells. Cryodestruction begins with freezing the extracellular environment, including the microvasculature. The rate of cooling defines the crystalline structure of ice. Increasing the rate of cooling allows more needle-like ice to form. Extremely rapid cycles of freezing facilitate the destructive processes that occur within the intracellular environment. A flash of extracellular ice rapidly forms around a single cell. At the 2 o'clock position and the 7 o'clock position on the screen, you see two channels within the ice. These channels will broaden as liquid is lost from the cell. The cell shrinks to a fraction of its original volume and becomes dehydrated. Only the extracellular environment is frozen at this point. As the extracellular environment warms, melting begins, and the dehydrated cell finds itself within a hypotonic environment. Water rushes back into the cell at a rate greater than was extracted, causing its size and volume to increase well beyond its previous state. The cellular membrane ruptures and expels the intracellular contents. Cell death has occurred. In a group of cells, a rapid wave of extracellular freezing moves across the screen. As the temperature decreases, flashes of intracellular freezing occur. This effect is due to the rapid cooling and extreme cold temperature. The cells do not have enough time to effectively dehydrate, therefore intracellular ice forms inside the cell. With rapid cooling and intracellular freezing below -50 degrees Celsius, further devastating effects occur to the structure of the cell. At the 7 o'clock position on the screen, we see the ejection of both structural materials and bubbles from the cell through the membrane. A single cell is identified during a rapid extracellular freeze. Ice penetrates the cell with this explosive action, allowing intracellular ice to form at a much more rapid rate than in the extracellular environment. The rapid formation of intracellular ice causes an increase in volume of the cell due to the expansion of ice. As ice continues to form, gases such as carbon dioxide, already dissolved in the fluids of the cell, become highly concentrated. Bubbles form, creating an internal force that drive themselves and other structures out of the cell, causing more rupture of the membranous structure. The same event with another cell shows rapid cooling of the extracellular environment. This rapid freeze extracts the water content of the cell so quickly that the membranous structure ruptures and bubbles of gaseous material push their way out of the system. Ice will continue to form and move in through the opening in the membrane, allowing the contents within the intracellular environment to become frozen. As warming begins, we observe the effect of thawing the cell. First, the extracellular environment melts, and as the intracellular environment is melted, the cellular structure fractures and the membrane peels away.